Hey, this is Mr. Rodriguez. I'm going to be going over the 10 problems from the worksheet that you guys got. I'll show you the method by which I work with my students, so if it doesn't really appear the same way as your teacher, maybe they can clear it up for you. Um, Number one, what are two ways to decrease the force of gravity between two objects? Specifically, if we look at the equation, F equals G m1 m2 over r squared. This tells us that the three factors are g, the force of gravitation, either the masses or the distance. Well, since g is a constant, we can't really change that. That means we can only change mass or the distance between the objects. To that effect, a mass decrease, right? Because specifically we're looking for ways to decrease the force. A mass decrease will decrease the force, right? If we make it smaller, if we decrease how much there is, the force will get smaller. The distance, however, if we make it longer, farther apart, so increasing the distance, remember it's an inverse relationship, increasing the distance will decrease force. So for number two, it's actually the opposite. It says increase the force of gravity. Since we've already established that mass and the distance between them, which is r, are the two things we can change for mass, decreasing the sorry, a mass increase will increase the force, and distance, if we shorten it and make it closer together, right? So a distance decrease, bringing them closer together will increase force. The force F. For number three, how does an increase in only mass affect the force of gravitation between two masses? So we're specifically asking two things, and the second question was, what about if only the distance increases between them instead? So we're just kind of really applying numbers 1 and 2. If we only increase mass, then the force of gravitation will increase. That's the first part. Second part, if you only, geez, my spelling is off today. If you only increase the distance, which means they're getting farther apart, right? Remember, understand that increasing the distance means they're getting farther apart, then the force will decrease. The next one, it says two planets in a distant solar system exert a gravitational force on each other. If the distance between them two planets was reduced so that they were now just 1/3 of the original length apart, then determine whether this change increases or decreases the force as well, and by what factor the force changes. So looking at our equation, remember we're saying that in our equation F equals G m1 m2 over r squared, assuming the rule of 1, that where everything initially starts off as 1, then that is going to equal 1, right? That's our established starting point. Looking at the individual components and how they change, G, m1, m2, and r. G is a constant, so it stays a 1. M, it tells us the distance between two planets was reduced, so they're now just 1/3 of the original length apart. Right? Reducing should increase the force. We know it's going to get closer together. So R is going to be 1/3 of the original length apart. Then determine whether this change increases or decreases the force as well. So it looks like we're not changing any of the masses here. So if there's no change to the masses, this tells us that m1 and m2 will stay at 1. So now we take these values, we see how things change. G stays a 1, M1 stays a 1, M2 stays a 1, and then we've got this all over 1/3 squared. Be real careful when you plug this into a calculator. You should get 1/1/9. Plugging that in to a calculator, it'll tell you something like 1/0.111111, and so on. But if you actually finish this off and go through the process of 1 over that value, you're going to see that it's 9, which is actually an increase in force, so 9 times greater or stronger a force. For the next one, we have planets floating in space or asteroids with we're just seeing how things change up. We already know that rule of 1 states they should be 1, but we're measuring how everything has been altered. Once again, G is a constant. It stays a 1 always. The first mass increased by 3 times as much, while the box reduces its mass to half its original size. So that's going to literally be 1/2. So we got M1 increasing it, M2 decreasing it, so you can't really make a prediction yet. It tells us the distance is unchanged. Remember, if something doesn't change, it stays a 1. Taking that, we've got G is 1, M1 is 3, M2 is 1/2, and then R is 1. Square that. This is going to end up giving us 1.5 over 1, and that simply reduces to 1.5. That's greater than the original force of 1. Should be a 5. Sorry if it looks like an 8. Simplifies to 1.5. So that'll be 1.5 times greater force. It's really important you understand whether it's greater or weaker than before. All right, the next one. If the distance between two objects is quadruple, so that's the distance, right? And just one mass is doubled while the other mass stays as is, what is the effect on the original 30 Newton force? So we're going to go a little bit further this time. Same as before, and I'll just keep writing the equation. So you can remember, since we're still learning and practicing, what the equation is. M1, M2, and R. How those are changing. G is 1 as always. One mass is doubled, so it doesn't matter which one it is. We'll go with M1 if the one being doubled, so M2 staying as is. If you stay as is and you're unchanged, that's a 1. And then it tells us that the distance is quadrupled. Quadrupled means 4 times, so that's going to mean that we're making it farther apart. So R is going to be 4. Taking all that information, now we plug it into the original equation to see how it changes. It's 1, 2, 1 over 4 squared. That's going to be 2 over 16, which is reducing to 1 over 8, which is going to be about 0.125, which means that the force is going to decrease, right? That's 0.125 times weaker. If the original force was 30 newtons, then it's 30 newtons times that factor of 0.125. And I believe that is going to end up being, get my calculator out real quick. 3.75 newtons. All right, the next one, number 7, 2 stars in space exert a gravitational force of 1,000 newtons on each other. If the distance between the stars was reduced so that they were now distance is now half as far. First star increases 5 times as much, while the second star reduces to only a quarter of its original size. What is the effect on the gravitational force? Right, we've got our equation. Know what happened there. M1, M2 over R squared. Got G, M1, M2, and then R. We're observing how those things change. G, once again, always a 1. Always, there's no reason it should be anything different. M1, if we go down in order, the first star increases its mass 5 times. That's going to be a factor of 5. While the second star reduces to only a quarter of its original size. You could write, that's like 1/4 or preferably 0.25. I prefer decimals, but go by whatever works for you. Just make sure you plug it into the calculator right. And then R tells us the distance was reduced, so they're now just half as far. They're getting closer together. So that'd be like a half or 0.5, whatever you prefer. Taking all that information and plug it in. G is 1, M1 is 5, M2 is 0.25, putting that all over 0.5 squared. Okay, and what we're going to see there is we're going to get, what is it? I believe that's going to simplify to 1.25 over 0.25. It's going to be 1.25 divided by 0.25, which reduces simply to 5. So that's going to tell us the force grows or increases, right? 5 times stronger, 5 times the force, increasing. So we're going to take our original force of 1,000 newtons. Then this time we multiply it by the factor that we got. It's going to give us an end result of 5,000 newtons. So 2 components. Next one, it says, how does the gravitational force change between the objects from its initial to its new conditions? So this one's a little bit tough because you have to observe how things are changing from when they began to how they ended up. So we got to look at each individual thing here. You don't have to label them. I will for the sake of the video. I'm going to call this guy M1. We're going to call this guy M2. And then we just keep that consistent as we go across. We've got our equation. F equals G M1 M2 over R squared. I always recommend writing the equation when you do this so you don't forget that R is squared. Just people writing it down without ever looking at the reference might make that mistake. So I always recommend writing it down. That's why I do it too, to keep myself checked. We got our values there. We got G, M1, M2, and R. Going down that list, looking at everything. We know G is going to be a 1. Now we're looking to see how things changed. So we look at M1, and if we go over here and check it out, we'll see that M increased. So that should give us a whole number value instead of a fraction, because if we decreased our value, then we would be like 1/2. But this time we doubled. So doubling from M to 2M would mean that it's 2 times greater. Looking at the other mass, right over here, we'll see that the second mass also doubled. We went from 1M to 2M, that's twice as big, 2 times greater. So that factors a 2, and then looking at the distance, we got further apart, so that's also a factor of 2. So, let's be careful here. We're not saying that, we always write down what's on the new side. We're not always writing down what's over here. That's not the idea. We're looking at the change. So taking all that, we've got, plug it into the equation, 1 for G. First mass is 2, second mass is a factor of 2, and then the distance or the radius there is going to be 2 squared. Looking at all that, we'll get 4 on top over 4 on bottom, which is simply just 1. So even though we changed everything, right, we changed both masses and the distance, okay, there's no change in force since it stayed a value of 1. how does the gravitational force change between objects from its initial to its new conditions if it was originally 40 newtons? So now we're just once again elevating everything. F equals G m1 m2 over r squared is the equation we're using. G m1 m2 r. We're seeing how all those things have changed. So once again, m1 m2, that's how I'm going to assign them. We have our first mass looking over here. It increased, it doubled, it's a factor of 2. Looking at our second mass over here, that mass is now 3 times greater. It tripled, so it's going to be a factor of 3. Looking at the distance, it did not change, right? There is no change. That's key then, right? Because we're not going to be able to write 2 down here. If it doesn't change, and it's a 1, just like our gravitational constant, right? Gravitational constant G never changes. That's why it's always a 1. So we're always looking to see how it changed. You can't just write 2 for M1, 3 for M2, and then 2 for the radius. We don't go by the numbers that are over here on the right side for new. We go by how it changes. So we're going to take that information. G is 1, M1 is 2, M2 is 3, and the radius is 1. We square that as the equation tells us to do. We'll get 6, it's weird, 6 over 1, which is 6. That means the force, or it's, force is 6 times greater. Taking that, we're going to multiply it by the original 40 Newton force. So 40 newtons is the original force. It's now 6 times greater, which is going to end up with 240 newtons. And now last but not least, how does the gravitational force change between objects from its initial to its new conditions if it was originally 50 newtons? All right, so looking at everything, you can kind of have a handle on what we're doing here. So we're going to have G, M1, M2, R. This first guy's going to be M1, this second guy's going to be M2. We have our difference. Looking at how things change. M1 decreased, so it's half as much, or 0.5. Remember, you can go by decimal or fraction. I prefer decimal. We have M2. M2 increased, it's doubled. We get that whole number of 2. Looking at our distance, we went from 2D to D. So ask yourself, did that increase or decrease? Right, since it decreased, we should get a fraction, right? Whenever we decreased our mass, we ended up with a fraction. So decreasing the distance, we decreased it by a factor of 2. But if we wrote down 2, that means it would have increased. So it's actually going to be half as much, or 0.5. It might seem a little bit tricky, but that decrease in the distance tells us we're going to end up with a fraction value. Just like M1 was a decrease, we have a fraction or decimal value. So taking all that, G is 1, M1 is 0.5. Remember, I preferred the decimal over the fraction. And then M2 is 2. Put that all over 0.5 squared. Plugging that in, 0.5 times 2 is 1 over 0.25. If we finalize and plug that in, 1 divided by 0.25 is going to give us 4. Remember, always follow through. Since 4 is greater than our original condition that the force started as 1, we're going to say that it's 4 times greater force or stronger force, however you prefer to word it. So now we just take our original condition where the problem told us the original force was 50 newtons times 4. It's going to give us 200 newtons. All right, and that's it. That's everything.